parent functions. So the parent function for a logarithmic function is f of x is equal to log of x. A logarithmic function is the inverse of an exponential function. Using your graphing calculator, sketch the following graphs. Now just pause here, pause the video here, and then just do these in your calculators and then verify that you get something similar to mine. So what you should get is your two functions should look something like this. Okay, that's log of x, and then we've seen this one before. Okay, and I'm just gonna highlight my two intersections there. We know that the exponential function, we always had y-intercepts. For the log function, we're only gonna have x-intercepts, because you'll see how that works out with our asymptotes once we get to our examples. For or next little part here, because you can only graph base 10 logs on your calculator, you will need to use the inverse exponential function, then invert the values from the table to graph the logarithmic function. So maybe pause the video and refresh yourselves with how inverses work, because you're going to need that skill, or you're going to be using that skill a lot to find our graphs of log functions. For our first example, it says graph each function and identify its key characteristics. So I'll be using this idea here, okay, relating the two, the log and the exponential function. Okay, it says graph f of x is equal to log base 2 of x. So the exponential function would be f of x is equal to 2 to the x. I would do my table just like before, x and y. Okay, I take some values to the left of the origin, some to the right, so -2, -1, 0, 1 and 2, and I plug those in to this function here. Okay, and once you do that, you're going to get 0.25, 0.5, 1, 2, and 4. So f of x, again, it's log base 2 of x, and it would be the inverse of this exponential function. And remember, what you do is you change the x and y, you flip the values. So then if x is -2, in this one it would be my y. So -2, and again, just follow through with the column. Okay, I flip my x's and y's. So 0.25, 0.5, 1, 2, and 4. And these are the points you're going to plot here to give you the log function. Okay, my x is 0.25, -2, so I'm like somewhere there. Negative, whoops, this is 0.5, looks like -5, so 0.5 halfway, -1, so it's like right there. 1, 0, it's right here. 2, 1, it's right here, and then 4, 2, it's right there. So then connect these dots. And then this is what my log function looks like. Now, if you keep plugging in, or if you were to look at our first table here, if you kept plugging in x values that kept getting smaller, smaller into the negative side, so -3, -4, -5, and so on, you're going to keep getting a smaller and smaller y. It's never going to cross 0. It's going to keep getting closer and closer to 0. So if you take the inverse values, you flip your x's and y's, it's going to hold the same way. Okay, so your x's here are going to get closer and closer and closer to 0, but never actually cross. Okay, so your asymptote here is this vertical line at x is equal to 0. And again, same thing, because you're going to keep getting you're going to get closer and closer and closer to 0, but never actually get there. Okay, so x is equal to 0. That's my asymptote. My x-intercept, you can see that I didn't cross my y-axis, but I do have an x-intercept right here. And if you look at my table, it's 1, 0. Notice my end behavior is changed. They want to know, and the way you read it as just go, if f of x is going to infinity, because this is going to just keep, it looks horizontal, but it keeps going up and up and up here. Okay, x goes toward infinity because x goes in this direction, so that's infinity. If f of x goes towards negative infinity, just going downwards, x is going to keep getting closer and closer and closer to my asymptote, which is 0. Okay, my range is, if you notice, my graph here goes down and it goes technically up as well in all directions of my y here. So my ranges are real numbers. My domain is clearly all x's from here going to the right side. Okay, so no negative x's here. So my domain is all x's greater than 0. Number 2, same thing. My exponential function is f of x is equal to 1/3 to the x. So if I do my table, and you notice that my b here is less than 1, so we do have exponential decay. So some values to the left, some values to the right of the origin, and plug these in here, and you're going to get the following values: 9, 3, 1, 0.3, and 0.1. These are repeating decimals. So inverse, right? And maybe we can add arrows just to kind of just denote that we're taking the inverse, switching my x's and y's. Whoops. Okay. So then my inverse here would be to switch my x and y values, and this would be the log 1/3 of x, base 1/3 of x. So I get 9, -2, 3, -1, 1, 0, 0.3, repeating decimal 1, and 0.12. Plot these points, and I get, let's see, so 9, -2, I'm right here, 3, -1, there, 1, 0, there, 0.31, it's very close, but around there, 0.12, this one's even harder to plot, but it's like even closer. Connect these, and you're gonna get something like this. Okay, and same thing, maybe we could start from the bottom. You can see that your asymptote is again x is equal to 0, because it gets closer and closer to the y-axis, but it doesn't actually cross it. Okay, and then that vertical line, the y-axis, that vertical line is x is equal to 0. My x-intercept, you can see from the table, it's 1, 0. F of x does go to infinity. Again, what does x approach as f of x goes to infinity? You can see that x has to get closer and closer to 0 to see this type of behavior. As f of x goes towards negative infinity, it looks horizontal, but this line technically will keep going down and down. X would go this direction, so towards positive infinity. My range, this function goes up and down everywhere, so all my y's, it's all real numbers. And then my domain, you can see that it's all x's from here to the right side, so all x is greater than 0. Next examples, I have log, let's see, log base 4 of x minus 1. So if I'm going to use my tables, so I have x and y, maybe we can see it as transformations of the exponential function. So f of x is equal to, and taking it from our previous one, we have base 4 of x minus 1. This here tells me I'm gonna translate to the right 1. So let's see, maybe I'm deciding what I want to show here because I'm gonna run out of space. So I'll just go ahead and let's plot, or let's show in my table, this first one, what would be my inverse table already. So not to confuse anyone, what I'm saying is that table I'm going to be doing for example 3 is the second one that I've done in the previous two, okay, the inverse already. Okay, so what would normally go on my x column, which is -2, -1, 0, 1, 2, I'm going to go ahead and put it on my y column already. Okay, -1, 0, 1, 2. Then maybe I shouldn't have written this in here because this is technically not the table. Let me write it in red, and if you're listening to this video, okay, you won't be confused. This is not the function for this one, right? This is technically this one, log base 4 of x. I'm not considering my transformation of moving one to the right yet. And this is again the inverse table already. So when you plug in, let me see, when you plug in -2 as x into this one here, you're going to get 1 over 16. And 1 over 16 is, let's see, 1 over 16. You get about 0.06. So 0.06. I'll write it down here better because I'm not feeling too confident with my explanation here. So this is technically f of x, 4 to the x, the inverse, so log base 4 of x. This table again represents the inverse of this one. So when I plug in -2 as x here, I get 0.06, and then when I plug in -1, I get 0.25. I get 1, 4, and 16. So again, when I plug in these as my x's, I got these values, and then I took the inverse, okay, which is log base 4 of x, and I get this table. Then I'm going to take this into consideration, which is represented by this as the exponential function, which means move to the right 1. Okay, so now that I have those x values, I add 1 to each of my x's because it's a horizontal shift. So I get 1.06 plus 1, okay, 1.25, 2, 5, and 17. And then my y is -2, -1. These don't change. 0, 1, 2, because there was no vertical shift. So then plot these points now. So 1.06 is -2, so approximately right there. 1.25 is -1. So just do your best to to plot those points as accurate as possible. 2, 0, 5 and 1 right there, and 17 and 2. It's not going to fit. You can go ahead and just try and plot it somewhere. Let me see. Let's see. Y is going to be 2. No, let's just leave it like that, and then just it's going to be something like that. So then you can see that, and just observe the pattern here, that if you kept increasing or kept going into the negative side here, -3, -4, -5 and so on, your x is just going to keep getting closer and closer to 1, but it's never going to go smaller than 1. So my asymptote here in this case would be x is equal to 1. You can also observe the graph in your calculator if you put this in your calculator. Actually, no, disregard that. You can't because you have base 4. But if you go back a few tables, like this one for example, before we took the inverse, you can see that you get closer and closer to 1. So then your asymptote would be at 1. My x-intercept, you can tell from my table, it's 2, 0. And then as f of x goes towards infinity, right here, x would have to go toward infinity. As f of x goes to negative infinity, x has to approach 1. My range, it goes up and down everywhere, so it's all real numbers. And then my domain is, you can see that from the asymptote, it's to the right, but x 0 is not included, so my domain is all x's greater than 1. For number 4, let's see, I'm going to go ahead and plot that second table already, similar to the previous example. So it's the inverse table, okay? Inverse table of the parent exponential function of this one here, okay? I'm going to avoid writing this in because I don't want to throw off any students, okay? So what would be the x's that I would plug in would be -2, -1, 0, 1, 2, and again this is my inverse table, so I'm already switching my x's and y's. When you plug these values in to 3 to the x, the would-be y values you would get would be 0.1, 0.3, these are repeating decimals, 1, 3, and 9. Okay, so again these would be, let's see, I guess I will write them out. F of x is, and the parent function here would be 3 to the x, and then this is log base 3 of x. Okay, and again, not to confuse any students, this table represents log base 3 of x, okay, but the table that would precede this one, the one before it, so when these were my x values, I would plug into here, and then these would be the y values I get from this. Then when I switch the x's and y's, I get the table for this one. Now my next table takes into consideration the -2 I have at the end. Okay, this would be a downward shift of 2. Okay, so we could say like down 2. So then my x's do not change. 0.1, 0.3, 1, 3, and 9. Again, because it's not a horizontal change, it's only a vertical change. So I have -4, subtract 2, -3, -2, -1, and 0. These are the points that you're going to plot. So 0.1, -4. I am down here. negative 0.3, negative 3, a little bit closer to the center, 1 and negative 2 right there, 3 and negative 1 there, and then 9 is on here, 6, 9, 9, 0 right there. Okay, so these are the points, connect them. Okay, and then that's my log function here. My asymptote, you can see that my x's keep getting closer and closer to 0. So x is equal to 0. My x-intercept, you can see from my table, it's 9, 0. As x goes to something, f of x goes to negative infinity. So here's negative infinity going towards negative. X has to approach 0. As x goes to infinity, f of x goes to infinity. My range, because this function goes up, down, everywhere, it's all real numbers. My domain, you can see that it's all x's to the right of 0. Number 5, I have log base a half of x plus 9 plus 4. So we would have here, and this table gets even more trickier to show. Let's see. We have half to the x plus 9 plus 4. This is the exponential function of this function here. So again, I'm going to show the inverse table. Okay, so when I would plug in -2, -1, 0, 1, 2 to this as my x, I would get the following y values. I would get 4, 2, 1, 0.5, and 0.25. Okay, again, when I would plug these in for my x's, I would get these for my y's. So then again, this is my inverse table, so I switch my x's and y's, and this is what my table looks like now. This table here represents the following log base a half of oh, and this is incorrect, sorry, this is the parent function. So sorry, these are the x values when I plug in here, and these are the y values I would get. Okay, so this is log base half of x, and then now I can consider this here. Okay, 9 would be a, let's see, let's draw my arrow here and let's describe. The 9 is plus 9, so it's to the left 9. I plug in the negative, so left 9, and then the plus 4 at the end is up 4, so up 4. So my x's, I subtract 9 from each of them, and then for my y's I add 4. So I get negative 5, negative 7, negative 8, negative 8.5, and negative 8.75. My y's, I get 2, 3, 4, 5, and 6. Plot these points carefully. You're gonna get, let me see, this one's the more tedious. There's 1 point, there's my other point, 8.5, it's midway, I get 6, negative 8, I got 4, negative 8.5, I get 5, 8.75, I get 6, so closer and closer. There you go. So Okay, so maybe I haven't explicitly said it, but your focus for log functions would be like the x-intercept, and of course the asymptote, which would be a vertical line. You can see from your table here that you're going to keep approaching -9, so that's going to be your asymptote. My x-intercept would be where does this log function cross the x-axis when y is 0, right? Because along the x-axis all y's are 0, all these points. So and let's see, one way you could go about this is maybe just backtrack and then see which the inverse points, 0, 7, which one would be 7, 0 for your x-intercept. And then as f of x goes towards -infinity here, okay, x has to go towards the positive infinity side. And then as f of x goes towards positive infinity, x is going to get closer and closer and closer to this value here, -9. Okay, my range is, again, goes up, down, everywhere. It's all real numbers. And then finally, domain would be all values to the right of that asymptote. So all x is greater than -9. For number 6 here, same thing, same one as number 5. I won't complete this problem here, but you can see that the transformations that you would have to keep in mind is you go to the right 2 and then you would go up 1. So same idea, plot your inverse table to the parent function and then apply 2 to the horizontal, so add 2 to all your x values and then add 1 going up. Add 1 to all your y values because you're going up. And that wraps up concept 45.